Our method of labeling trees starts with a lemma which is commonly known as type 1 transfers, or edge transfers. In edge transfers, we transfer two branches from one vertex, u, to another vertex, v. The two branches are extensions of two neighbors of u, u sub 1 and u sub 2. And this process can be completed if w of u sub 1 plus w of u sub 2 equals w of u plus w of v. In other words, the sum of the weights of the start vertex and the destination vertex must equal the sum of the weights of the two neighbors of the start vertex. Here's an example of an edge transfer from the vertex with weight 5 to the vertex of weight 10. We can do this since 5 plus 10 is equal to 12 plus 3. A more specific process that we use is the backward double A transfer, a series of 7 consecutive type 1 transfers on 4 consecutive parent vertices. Let's see how this process works. We will perform the BD8T on the parent vertices with weights 14, 1, 13, and 2. First, we transfer the children vertices with weights 4 through 11 from 14 to 1. We can do this since 14 plus 1 is 15, as is 14 plus 11, 5 plus 10, 6 plus 9, and so on. Next, we transfer the vertices with weights 4 through 10 from 1 to 13, as pictured. Third, we transfer the vertices with weights 5 through 10 from 2 to 13. Fourth, we transfer the vertices with weights 6 through 10 from 2 back to 14. This concludes the first 4 steps of the BD8T. In each of these steps, as many vertices as possible are transmitted from one parent to the next. Now, we will begin the second stage of the BD8T. Vertices with weights from 6 to 9 are transferred from 14 to 1, leaving only the vertex with weight 10 on the parent labeled 14. Notice that this step only leaves one extra child on parent 14. Again, we move vertices 6 through 8, leaving only one child, child 9. Finally, we move vertices 7 through 8, leaving only child 6 with the parent. This concludes the BD8T. Our algorithm uses a series of edge transfers and BD8Ts to leave the desired number of children with the parent at each step. Our algorithm first defines counting functions on the parent vertices of the trees. Each vertex is assigned an original counting function, or OCF, and at any given time, 4 vertices have a positive counting function, or CF. The rules are described here. A parent vertex is an odd parent if it has an odd number of children, and likewise for even parents. If the first parent is odd, give it an OCF of 0, otherwise it has an OCF of 1. If 2 consecutive parents have the same parity, they have the same OCF. However, if they have different parities, their OCFs will differ by 1. If step 3 is performed on the previous 4 parents, then the larger indexed parent of the pair has a lower OCF. If step 3 isn't performed, then the larger indexed parent has a higher OCF. Step 3 is a check that is performed on every 4 consecutive parents. If they all have a positive CF, then all 4 of their CFs are decreased by 1. We repeat steps 2 and 3 repeatedly until the process terminates. That was a lot to take in, so let's try an example. In the given tree, the parity of each of the parents is shown. The first parent is odd, so we assign it an OCF and a CF of 0. The second parent is even, a different parity, so its OCF is 1, which is 1 more than 0, the OCF of parent number 1. This is because step 3 has not been performed. It also has a CF of 1. Again, the third parent is a different parity, so its OCF and CF are both 2 because step 3 has not been performed. The fourth parent is a different parity as well, so its OCF and CF are both 3. Finally, the fifth parent is a different parity as the fourth parent, so its OCF and CF are both 4. Now we have 4 consecutive parents with a positive CF, so we decrement each of them before moving on to parent number 6. Parent number 6 has the same parity as parent number 5, so it also has an OCF of 4. We again perform the quadruple decrements on parents 3, 4, 5, and 6. Parent number 7 has the same parity as parent number 6, so it also has an OCF of 4. We again perform the quadruple decrement. Parent number 8 again has the same parity as the previous parent, so it has an OCF of 4. We perform one more quadruple decrement. Parent number 9 has a different parity than parent number 8, so has an OCF of 0 minus 1 equals 3, because the decrement had been performed. However, we can still perform the decrement on parents number 6, 7, 8, and 9. Now parent number 10 has an OCF 1 less than parent number 9 because they are different parities, so its OCF is 2. Again, we perform the decrement. Finally, parent number 11 has an OCF of 1 because it is a different parity than parent number 10. We perform a final decrement, and the process terminates as all counting functions are 0.